Welcome to the lecture on piecewise defined functions. This section is on functions that do not have a single rule. They're defined in pieces, and this first example gives you an idea of what we're going to be working with. We have f of x, and then you see these this big curly brace, and that defines the two different rules that this particular function has. We're going to use the rule 3x plus 4 for all x is less than 0, and we're going to use the rule negative x plus 2 for all x is greater than or equal to 0. So the first thing we need to be able to do with these piecewise defined functions is evaluate them. So if you see, for example, f of negative 4, remember that negative 4 is your input value, and so that's your x. And so this is saying what is y when x is negative 4. So when we have a piecewise defined function, what's important to figure out is which rule are you supposed to use. And you look at the input value based on these two conditions over here to determine which rule is appropriate. So if we have an input x that's equal to negative 4 is less than 0, so we are going to fall in this condition right here, which means we want to be using the top rule. And so we're going to use 3x plus 4 and substitute in negative 4 for this x. So this is going to be 3 times negative 4 plus 4, which simplifies to negative 12 plus 4, or negative 8. Okay, the next example we want f of 3, so this time we want our x value to be 3. So if we look at our two conditions, we have 3 is greater than or equal to 0, so this time we want to be using the bottom rule, so that we're going to plug in 3 for this x and get negative 3 plus 2, which simplifies to negative 1. And finally, f of 0. 0 is going to fall in which of these two conditions? The top one is x is strictly less than 0, and the bottom one is x greater than or equal to 0. So because of that equal bar, we need to use the bottom rule. So if I substitute in 0 for this x, I would get negative 0 plus 2, which is just going to stay 2. One of the most common mistakes that I see in examples like this is students giving me two answers, the answer for the top rule and the answer for the bottom rule. You need to decide which one is the true answer, and you determine that by looking at your restrictions on x over here to the right. Only one of them is going to apply, so you have to look at your restrictions over here to figure out which rule you're supposed to use. Okay, so the first thing you need to be able to do is evaluate these piecewise defined functions. The second thing you have to be able to do is graph them. And that can be a little bit tricky sometimes since we have two different rules. So if we look at our rules again, we have two separate equations here, and I'm going to just start with the top one and graph that first. And this is how I like to do it. This is the rule for x is less than 0. And when x is less than 0, we're supposed to use the rule f of x equals 3x plus 4. Well, remember, f of x is the same as y, so this is really like the equation y equals 3x plus 4. And you should know how to graph that because that's just a line. But when we graph this, we don't want to graph the entire line. We're only supposed to graph it for the x's that are less than 0. So 0 would be this y-axis. That's when x equals 0. Less than 0 is going to be to the left of that line. So we should only be graphing this line in quadrants 2 or 3, over here on the left side of the y-axis. So to get the right graph, what I like to do is I make a little table, and I use this point right here, this number that's in this condition, as one of my x's, since that's kind of an important point. In this case, since we want all the x's less than 0, this is going to be our stopping point. This is where our line is going to stop. So if I let x be 0, let's plug that into our equation to find out what y should be. So if I plug in 0, 3 times 0 plus 4, this goes away, and we just get 4. So 0, 4 is one important point on this graph. Now, because this is a line, we need 2 points to graph a line, so I need to pick another x. And here is where you want to be very careful. Since we only want x's less than 0, make sure that you pick an x that is smaller than 0, so something negative, like -1. So let's plug in -1 into my equation. 3 times -1 plus 4 is going to give me -3 plus 4, or +1. Now when I'm going to go and plot these 2 points. 0, 4 would be right here, and -1, 1 would be right here. And the line between them initially would look like all of this. However, remember that we only want the line for x is less than 0, so I'm not going to graph that whole line. I'm only going to graph it from 0, which was this point, 0, 4, and to the left for x is less than 0. So this 0, 4 is like your stopping point, and we want to just go to the left from there. Now one more thing that's really important is right at 0. This was supposed to be the rule for x is strictly less than 0, so we don't actually want to include the point that occurs right at 0 since this didn't have an equal bar. So 0, 4, what we're going to say is we should have an open circle at that endpoint. So if I take my, oops, too much. If I take that 0, 4, I'm going to put a little open circle at 0, 4 and draw my line just as I had before between these 2 points. But notice that I'm not including that stopping point because there was no equal bar in my inequality. Okay, so that's the first rule. We only graphed it for x is less than 0. Let's see how to graph the top one, or the bottom one. The bottom rule was f of x equals -x plus 2 for x is greater than or equal to 0. So we want this to be for x is greater than or equal to 0, and the rule that we're going to use is f of x equals -x plus 2. I'm going to think of f of x as y, so this is going to become y equals -x plus 2. So here's my second graph that I want to make, and remember that we're just going to make a little table here, and one very important point that you always want to look at in your table is this breaking point, this little determination right here, x greater than or equal to 0. So I definitely want to see what happens at 0. If we plug 0 into our rule, we're going to get -0, which is going to stay 0, plus 2. So this is going to be 0, 2. Now notice in the inequality, this had an equal bar. So this time we do get to plot that actual point, and this is going to have a closed circle around it. So when I go to 0, 2, I'm going to put a solid little dot right there. Whoops. So we're going to have a dot right here. Now for a second point, so that I can graph the rest of my line, we want to make sure that in our table we're only picking x's that are greater than or equal to 0. So this time I want to make sure I pick an x that's bigger than 0, like 1. And if we plug in 1, we're going to get -1 plus 2. -1 plus 2 is 1, so we can also plot the point 1, 1, which would be right here. And now when we go to connect our line, make sure that you don't go past 0. At 0 is actually the starting point of this line, and now I'm going to graph the line going towards the right. So we have the blue line going to the left, that's for all the x's less than 0, and the red line going to the right for all x's greater than or equal to 0. And so this is our final graph, these two pieces put together. Okay? So piecewise defined functions, they can have some complicated graphs. Making sure that you graph each rule separately, making sure that you look at whether you need to have an open circle or a closed circle, and only picking x values that are appropriate for the range that you're working with is going to be key when you're trying to make the correct graph. So let's try another example. Alright, this function, g of x. g of x is -1 if x is less than or equal to 0, and g of x is -3 if x is greater than or equal to 2. Okay, so the first thing we're going to do is evaluate some function values. Just get practice using this function. So if I want g of negative 5, then that means the x value is supposed to be negative 5. So which of these two domains here does that fall into? We've got x is less than or equal to 0 for the top rule, and x is greater than or equal to 2 for the bottom rule. Well, since negative 5 is less than 0, that means we want this top domain, which means we want to use the top rule. Now notice here that this particular function doesn't have an x in its rule. That means it's a constant function. It's independent of x. It's always going to be equal to negative 1. So even though we have an x that's negative 5, we have no x to plug that into. So this output is going to always be negative 1, no matter what this x value happened to be right here. So this is a constant function, so my answer is just negative 1. For the second example, we want g of 0. So this time we want our x to be 0. We need to know what x is first so we can determine which rule we should use. And x equals 0 is included in this equal bar right here. So that means we want to use this top rule again. And remember, this rule is independent of x, so it doesn't matter what x is. The output is always negative 1. So this is also going to be negative 1. For the last example, we want g of 5. So this time we want x to be 5. And 5 is greater than 2. So this time we are going to use the bottom rule. This bottom rule also does not have an x in it, so it's a constant. So no matter what your x is here, the output is always negative 3. So this answer is going to be negative 3. So there is our examples evaluating a function. Now let's talk about how we are going to graph this. So the first thing we're going to do is graph the top rule, and this was the rule for x is less than or equal to 0. So when x is less than or equal to 0, we're supposed to use g of x, which is y, equals negative 1. So when x is less than or equal to 0, we're supposed to be graphing y equals negative 1. You can graph that however you like. I'm going to make my tables again just to show you the importance of picking the right x values here. Remember that this domain was x is less than or equal to 0, so we definitely want to see what happens right at 0. So make sure you use x equals 0 in your table. We also want x is less than 0, so make sure that for your second x, you're picking something smaller than 0, something negative, like negative 1. Okay, so these are going to be my two x values that I choose. Remember, our function was y equals negative 1, and that doesn't have an x in it, so it doesn't matter what x's we had picked, the y value is always going to be negative 1 for both of these. So let's go ahead and start plotting these. Now this first one, 0, remember that had an equal bar in the actual inequality, so that means we get to include this point. So at 0, negative 1, we're going to have a closed circle. So 0, negative 1 would be right here, nice closed circle. Negative 1 would be right here. And when we connect these, remember that we're connecting them so that we're using only the x's less than or equal to 0. So 0 was this dot right here. Less than that would be to the left. So we're going to connect these 2 points going towards the left. And this is just a horizontal line at a height of negative 1. That stops right at that y-axis. So there's the graph of our top rule. It's just a horizontal line at negative 1 for all the negative x values and 0. So now let's do our bottom rule. So our bottom rule is negative 3 if x is greater than or equal to 2. So when we have x's greater than or equal to 2, we're supposed to use the rule g of x, or y, equals negative 3. So I want to make a little table again. This time my table is going to start at this value right here, which is 2. So I want to make sure that I use x equals 2. And I want x's that are strictly greater than or equal to 2. So the next x that I pick should be something that's bigger than 2. Like 3. So those are my two x values that I'm going to choose. And remember, my rule was y equals -3. There's no x in that rule, so it's independent of x. No matter what my input is, my output's always -3. So if x is 2, y is -3. If x is 3, y is still -3. So these are my 2 points that I'm going to plot. Because 2 had an equal bar in the inequality, that means I get to include it. So this 2, -3 point needs to be a closed circle. And that's going to be my starting point. So 2, -3 would be right here, nice closed circle. 3, -3 would be right next to it. And when we graph these 2 points and make a line out of this, we're only going to be graphing the line that has x's greater than or equal to 2. So here's 2, greater than or equal to 2 would be to the right. So I should be connecting these to the right. And both of these endpoints here are closed circles. So here's my graph. Okay, x less than or equal to 0 is going to the left. That was y equals -1. X greater than or equal to 2 is going to the right, and that was y equals -3. 2 horizontal lines, but we're not using the whole line, we're just using part of the lines. Okay, so there's my graph. Now one more thing we're going to do with this function is to review what domain and range would be. Now when you're trying to find the domain of a piecewise defined function, you can do it in 2 ways. If you've already taken all the time to graph your function, you can look at the graph to see what your domain is. Remember that domain is x's and range is y's. So we're looking at all the x's that got used in this graph. And if you look at your graph here, we used all these x's up to 0, then we kind of jumped and used all the x's greater than or equal to 2. So when we write domain for a nice connected graph like this, we want to be using interval notation. So the domain of this blue part, the blue graph, would be -infinity up to 0, and I included the 0 because of that closed circle, so I'm going to put a bracket around the 0. And then we kind of jump, we pick up at 2, and there was a closed circle at 2, so I'm using a bracket, and from there I went to the right, so I went up to infinity. And I want both of these, so I put a union symbol in between. So one way to determine domain is just by looking at what x's got used in your graph. Another way that's also pretty easy is to just look at your initial function. These conditions right here and right here tell you your domain. So the only x's I get to use here are x's less than or equal to 0, which would be -infinity to 0 with a bracket, or x is greater than or equal to 2, which would be 2 with a bracket up to infinity. So my domain is these two combined, so I just put a union in between. So it's really easy to tell your domain just by looking at the initial inequalities in your piecewise defined function. So that's domain. Now to find range, it's usually easiest to determine your range from a graph. So you kind of need to be able to be looking at a picture to see what your range is going to be. Remember that range is y's. So we're looking at all the y values that this graph goes through. Well, if you look at the blue graph, the only y's that this graph goes through is -1. If you look at the red graph, the only y's that this graph goes through is -3. So the only y's that the whole graph goes through is -3 and -1. And since those are just 2 distinct numbers, we are going to be using sets to describe that range. So this would be the set -3 and -1. I would not want to use an interval, for example, -3 up to -1, because that implies that I would be hitting all the numbers in between -3 and -1, like -2. This graph does not go through -2, nor does it go through any of those fractions or decimals in between. So don't use an interval for this particular example. We just use a set because I only went through 2 values for that range. Okay? So that one's kind of tricky. Alright, we're going to do one last example. We're going to have a new piecewise defined function. This one is a little more complicated because it has 3 rules. And we're going to start by first just evaluating the function at different values to kind of get used to how this function works. So if we start with our first example, we want f of 3, and f of 3 means that the x value we're looking at is 3. So if we go over to our domain restrictions over here, where does 3 fall into any of these inequalities? Well, 3 is bigger than 2, so that means we want to be using this bottom rule. And this rule has an x in it, so I'm going to be substituting in 3 into that rule. So this is going to be 2 times 3 minus 1, which gives us 5. So f of 3 is 5. We should only be getting one answer here because there's only one rule that will apply if x is 3. Okay, let's look at f of 0. This time we want x to be 0, and which rule, which restriction over here includes x equals 0? We have an equal bar right here for this 0. So 0 is in this top rule. So I'm going to substitute in 0 in for this x. So this would be negative 1/2 times 0, which is going to stay 0. So f of 0 is just 0. Okay, f of negative 3. This time we want x to be negative 3. So which rule should I use? Well, negative 3 is less than 0, so that's included in this top inequality. So that means we're going to use this top rule again. So we're going to take negative 1/2 and substitute in negative 3. Negative 1/2 times negative 3 gives us positive 3/2. Okay, and in the last example, we want f of 1, so we want x to be 1. So which inequality does 1 fall into? Well, 1 is between 0 and 2, so this time we're going to be using the middle rule, substituting in 1 for the x. So this is going to be 1 plus 1, or just 2. So that's how we evaluate our function. Now we want a graph. And this has 3 rules, so we're going to need to make 3 tables so that we make sure we get the right graph. So let's start with the top rule. This is a rule that we use for x's less than or equal to 0. And the rule is y equals negative 1/2 x. So I am going to make a table for that rule. And in my table, I want to make sure that I use this 0. And then for my next x, I want to make sure that I pick an x that's less than or equal to 0. So that would be something negative, like negative 1. Okay? And I'm going to substitute those in to the rule negative 1/2 x. So if we plug 0 into that, negative 1/2 times 0 stays 0. If I plug in negative 1, negative 1/2 times negative 1 becomes positive 1/2. Now 0, 0, that was this sort of endpoint right here. And because of the equal bar, that means we get to include it. So this should be a closed circle. So let's plot 0, 0 with a closed circle. Nice solid dot. And then negative 1 comma 1/2 would be right about here. Just estimate that. And we're going to connect these two dots with a line, but we want to make sure that we're only graphing for x's less than or equal to 0. So here was 0. Less than 0 would be to the left. So I only want to graph my line from 0 going to the left. My line here is a little off because my pen is a little bit finicky. So let's try this one more time. Here's negative 1 comma 1/2, and I'm only going to graph it going this way. So there's my first rule, that top rule. Alright, now let's try the middle rule. So this rule is going to be for x's between 0 and 2. And that equation that we're supposed to use is y equals x plus 1. Now this time, we actually see 2 points in my inequality, 0 and 2. So that's ideal for our table, because since this is a line and we need 2 points to plot, I can use 0 for one of them and 2 for the other one. So I have my 2 endpoints. And I'm going to only be connecting this line between these 2 points. 0 is kind of the starting point, and 2 is the stopping point. So if we plug in 0 into our rule x plus 1, 0 plus 1 would be 1, 2 plus 1 would be 3, and notice in my inequality there's no equal bars here. So both of these endpoints need to be open. So 0, 1, open circle, 2, 3, open circle, and we're only supposed to be graphing this line starting at 0 and stopping at 2. So we just get kind of a little line segment right there. And that's our middle rule. That's the middle portion of our graph. Okay? For the last one here, we have the x greater than 2, and we want to graph that for 2x minus 1. So I'm going to do a third table for x's greater than 2. Oops. So for x is greater than 2, and the rule is going to be y equals 2x minus 1. And I'm going to make a little table, and my important point here in the inequality was this 2, so make sure you start your first x at 2, and for our second x we want to make sure we pick an x that's bigger than 2, so something like 3. Now let's plug both of those into my rule 2x minus 1. So 2 times 2 is 4, 4 minus 1 makes this 3. 2 times 3 is 6, 6 minus 1 would be 5. So here's the 2 points I need to plot. Since 2 did not have an equal bar, this first point is an open circle. So 2, 3 is another open circle right on top of the other open circle we already had. Okay, sometimes in these piecewise functions, one circle is open, but then you have a second point that goes and closes it back up. In this case, we don't have that. We have them both being open. So 2, 3 is right there. 3, 5 would be right here, and that's going to be a closed circle. It's only the end point that is either open or closed. And now we want to connect these two purple dots, and we want to do it in the direction of x is greater than 2. So this was when x was 2, greater than 2 would be to the right, so I want to be connecting these going to the right, just like that. So we have our blue graph, our red graph, and our purple graph. And those are the 3 different rules in our piecewise function. Okay, so there's our complete graph. That's the whole function right there. Alright, to finish off, let's talk about the domain and the range of this same piecewise function. Domain is x's, range is y's, and remember there's an easy way to tell what your domain is. Just go back to the original function and look at the domain right from these inequalities up here. So my domain is all the x's that get included here. So x less than or equal to 0 would be the interval minus infinity up to 0, and because of the equal bar, we have a bracket around the 0. 0 to 2 would be the interval 0 to 2 with parentheses. They both have parentheses because there were no equal bars. And x greater than 2 would be start at 2 and go to infinity, and again a parentheses because there's no equal bar. So now we just want to put all these together, and notice that from minus infinity to 0 and then 0 to 2, I'm including the 0, so we could sort of combine these two into one more concise inequality. That includes all the numbers from minus infinity all the way up to 2, and then I keep an open parentheses around the 2 because it wasn't included here and it wasn't included here. So minus infinity to 0 and then 0 to 2 gives me the full interval minus infinity to 2. So I only really need one interval to describe these two put together. And then for the last one, we can add in 2 to infinity. Notice that this is really including all x's except 2, because we had a little hole right at 2. So if I go down here, my domain is minus infinity to 2 union 2 to infinity. And you should be able to see how that checks out on your graph here. Remember, domain is x's, so think about all the x's that got used. I used all these negative x's on the blue graph. I used all the x's from 0 to 2 on the red graph, and then I used from 2 on in the purple graph. The only point that never got filled in at one point, at any point, was right here at 2. At 0, this dot used 0. So The only number that never got used anywhere was 2, and that's why we had to leave it out of our domain. So here's our complete domain. Everything but 2. For the range, we want to think whys. So to find a range, usually it's easiest to find a range looking at a graph. And you want to think up and down, since that's your y values, going up and down. So what's the lowest y value that got used, that got hit? 0, because there's no negative y's that were ever plotted. And 0 was attained because there's a closed circle there. So the smallest y value that we have is 0. So this is going to start at 0 and include it. Now think about the highest y value that got used. Well, on this blue graph, I go from 0 and I keep going up, 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 up. So all these positive y values are going to get hit. It looks like there might be a little jump right here between 0 and this first little red open circle, but all these blue points right here on this blue line use those y values. So between 0 and 1, I am plotting some points because of my blue graph. So my range starts at 0 and hits every y value going on up. So my range is 0 to infinity. That one's kind of tricky to see from the graph, but it's really the range is being determined by this blue function. The red one and the purple one kind of double up points there and hit all these y values here and all these y values here, but those are also going to be hit by the blue graph as well. So your range, 0 to infinity. Alright, that concludes our lecture on piecewise defined functions. Good luck.